So to learn about moment of inertia, I'd like you to think first about torque. The amount of torque you have to apply to something to get it into rotational motion, or to keep it in rotational motion, or to stop it from rotating really depends on how heavy that object is, where the mass is distributed in the shape of the object, and how fast it's accelerating or decelerating in the first place. So that's where we get this equation. Torque is equal to moment of inertia times angular acceleration. So remember, angular acceleration is how many degrees it's moving with respect to time and with respect to time again. So that makes sense. If it's going really, really fast and you need to stop it, then it would be a really high torque to stop it, right? And let's look at the term I. I is moment of inertia, and it's a function of mass and the geometry. A lot of you know what a flywheel is. It's something that is meant to have a high moment of inertia so that once it gets going, it doesn't take a lot of torque to keep it going, doesn't take a lot of energy to keep that motion from happening. And a flywheel is a very useful device in mechanical energy systems. But think about if the mass is distributed at the far edge of a flywheel, really a large radius away from the center of rotation. Imagine how much energy it takes to stop that flywheel from spinning. Let's think about the application. Let's think about the application of a wind turbine also. So let's say a wind turbine has 3 blades. Now I'm going to attach a whole bunch of mass to this wind turbine. So I'm going to put a mass here, a mass here, and a mass here, mass M. And the wind turbine is going to rotate. So it has an angular acceleration. And let's think about the amount of torque we would have to apply to stop that system versus if we had a wind turbine that was built a bit differently and it had a lot of mass sitting at the outer radius. So this is a pretty dysfunctional wind turbine, and I don't recommend it. But say the mass is distributed further out and it's spinning with that same angular acceleration going on, then how much torque is it going to take to slow down wind turbine A versus wind turbine B? It's going to take a lot more torque to slow down this wind turbine than it would for this one. So again, they have the same mass, the same angular acceleration, but the mass is distributed in a different location with respect to the center of rotation. So we can take that equation. From above, and we can just rearrange it. So let's solve for I, moment of inertia, and let's look at what this moment of inertia term means. So again, I took that same equation that we knew before. I just rearranged it, and it's torque over angular acceleration. But we also know that torque is force times distance, and the distance that we're talking about is the distance from angular rotation point, which when we're talking about rotation, that distance is radius r. So here I'm taking the torque is force times distance, and I'm subbing in r for the radius. I'm also going to sub in something else, that force is equals mass times acceleration. And then acceleration, we can drill down as well. Acceleration is a linear acceleration. That's equal to the angular acceleration times the radius r. That is just like velocity equals the angular velocity at radius r. So these two things are true. So now I can sub in F equals ma, and for A, I can sub in omega r. So here they are subbed in, which gives us an r squared term. Let's take that and sub it back into this equation for torque. And so I did that here. And so I get m angular acceleration r squared over alpha was already in the equation. Now I can cross out those alphas, and I see that moment of inertia is equal to mr squared. So that's actually for a system with a point mass. I also want to show you that if you have a system, say, with 3-point masses, like I just showed on that system where I was sticking mass in different places, then the moment of inertia for the whole system is equal to the sum of the moment of the inertias for all of the parts of those point masses. Now, a fun exercise is to look at the derivations of other shapes. So here's the point mass one that we did above, and a quick internet search will show you what happens if you fill in an entire circle, and that would be basically a solid disc or a cylinder. And the interesting part is it'll take the same amount of torque to accelerate a cylinder that's very tall versus a cylinder that's very flat, like a flat disc. So you'll notice that the height of the cylinder does not matter in this equation. It does not factor in at all. And then it's a simple matter to figure out the moment of inertia for a cylindrical tube, because here you're just subtracting the inside of it, and the mass is further distributed towards the outer radius instead of the inner radius. And it's all about the placement of where that mass is. This is an interesting one. Let's say you had like a heavy steel rod. Try to rotate that about the center, and then try to rotate it about the end. Which one is harder to rotate? That one is the one that requires more torque. And you would find practically in real life, if you were to try to do this, this would be easier. This would be harder to rotate. This one's harder to rotate. And you can see that the moment of inertia is lower here. You're dividing by a higher number versus this one. Moment of inertia questions are not that hard. You basically look at, well, what shape is the thing? And then you can sub in. So this one is a flywheel, which is basically a cylindrical disc. And then you can just substitute into whichever equation exists for that moment of inertia, which you don't have to memorize. You just have to know where to find them. And then you can have the moment of inertia, which will be useful in more equations later on, like it helps you calculate the power available from wind and water power. Here's a little bit more of a complex question, and this is one that we're going to work in our synchronous class, and I do have the solution for it, and we can take it up in class. And this one is a quite complicated one, and here's a hint for you that in this one you have to figure out the total moment of inertia is a sum of all of the moment of inertias of all of those parts. I'd like to do this one in class together as well.